China launches groundbreaking 3-satellite constellation pioneering Earth-Moon space exploration. Date, April 17, 2025. Introduction. In a remarkable achievement for space exploration, China has successfully established the world's first 3-satellite constellation operating in a distant retrograde orbit DRO within the Earth-Moon region. Developed by the Chinese Academy of Sciences CAS, this groundbreaking project is set to significantly advance future lunar exploration and utilization of deep space, marking a pivotal milestone in China's space endeavors. Background and development timeline. The groundwork for this ambitious project dates back to 2017, when the CAS initiated preliminary research and technological development concerning the Earth-Moon region. This led to the launch of a pilot project in February 2022 aimed at creating a 3-satellite constellation to explore the unique characteristics of DRO. The timeline of key events includes: February 3, 2024, the experimental DRO-L satellite was successfully launched into a sun-synchronous orbit, laying the foundation for the constellation. March 13, 2024, the DRO-A and DRO-B satellites were launched from the Xichang Satellite Launch Center. However, they initially encountered an anomaly in the upper stage of the carrier rocket, preventing them from reaching their intended orbit. July 15, 2024, after extensive corrective maneuvers, the DRO-A and DRO-B satellites successfully entered their designated orbits. August 28, 2024, the 3 satellites formed a complete constellation, establishing K-band microwave intersatellite measurement and communication links. Key features and technological advances. 1. Distant Retrograde Orbit DRO. The unique DRO allows spacecraft to maintain stability with minimal fuel consumption, acting as a natural hub for connecting Earth, the Moon, and deep space. 2. Fuel efficiency. The satellites achieved low energy insertion into the DRO using only 1/5 of the fuel typically required for such maneuvers, significantly reducing costs for future missions. 3. Inter-satellite communication. The constellation validated K-band microwave communication links over a distance of 1.17 million kilometers, a crucial technology for large-scale constellation construction in cislunar space. For satellite-to-satellite tracking, the project implemented a space-based orbit determination system, allowing one satellite to track another with precision comparable to traditional ground tracking, thus lowering operational costs and increasing efficiency. Applications and implications for future exploration. The establishment of this 3-satellite constellation is expected to play a crucial role in supporting future lunar exploration missions by providing space-based inter-satellite measurements and high-precision navigation services. The research team intends to investigate the complex orbits in the Earth-Moon region and conduct fundamental scientific research in areas such as quantum mechanics and atomic physics, leveraging the DRO's stability. The strategic importance of cislunar space for long-term human activities. Interplanetary exploration and resource exploitation is underscored by this development. The CAS emphasized that developing and utilizing cislunar space offers tremendous opportunities for lunar resource exploitation, enabling sustainable exploration of the solar system. Integration of sources and perspectives. Reports from multiple sources, including Xinhua Global Times and China Daily, align on the significance of the 3-satellite constellation as a foundation for future exploration. While Xinhua emphasizes the technical achievements and operational details, Global Times focuses on the strategic implications of cislunar space for long-term human activities. China Daily corroborates these points, detailing the technological breakthroughs achieved and their broader implications for lunar habitation and resource utilization. Conclusion. China's establishment of the DRO-based 3-satellite constellation marks a monumental milestone in space exploration. This achievement not only showcases advanced engineering capabilities but also sets the stage for a new era of scientific investigation in the Earth-Moon environment and beyond. As China continues to push the boundaries of space exploration, the successful integration of this constellation will undoubtedly contribute to the future of human habitation and exploration of the cosmos. China's recent establishment of the world's first three-satellite constellation in the Distant Retrograde Orbit DRO around the Earth-Moon region marks a significant milestone in space exploration. This achievement, spearheaded by the Chinese Academy of Sciences (CAS), showcases advancements in satellite technology and opens new avenues for lunar exploration and deep space missions. Counterintuitive insights. 1. Fuel efficiency and cost reduction. It might seem logical that launching multiple satellites would require more fuel, but the opposite is true for the DRO constellation. By developing a method that uses only 1/5 of the fuel typically needed for lunar transfer and insertion into DRO, this project demonstrates that innovative orbital mechanics can lead to significant resource savings. This efficiency contradicts the common assumption that larger missions incur higher operational costs. 2. Stability of DRO as a natural hub. While one might expect that orbits closer to the Moon would offer better operational advantages, the DRO's unique characteristics allow for greater stability and reduced fuel requirements for maintaining position. This highlights the counterintuitive nature of cislunar space dynamics, where a less direct path can actually yield more sustainable long-term operations. 3. Satellite-to-satellite tracking versus ground-based tracking. The notion that tracking satellites must rely on ground stations is deeply ingrained. However, the successful implementation of a satellite-to-satellite tracking system that provides orbit determination accuracy equivalent to 2 days of traditional tracking in just 3 hours challenges this assumption. This advancement suggests that technological evolution can overcome traditional paradigms, allowing for more flexible and efficient space operations. For broader implications for cislunar space, while many view space exploration as a primarily scientific endeavor, the strategic importance of cislunar space for future human habitation and resource utilization is underscored by this project. This challenges the idea that space exploration is only about science. Instead, it highlights the geopolitical and economic dimensions involved in space endeavors. 5. Complex orbits for fundamental research. The expectation might be that simpler orbits are more beneficial for scientific research. However, the complexity of the orbits in the Earth-Moon system, as explored through the DRO constellation, provides new opportunities for fundamental research in fields such as quantum mechanics and atomic physics. This suggests that complexity can lead to novel scientific insights rather than just operational challenges. 6. Intersatellite communication technology. The successful validation of K-band microwave communication links over a distance of 1.17 million kilometers could be perceived as merely a technical feat. However, this capability is not just about communication, it fundamentally changes the game for future satellite constellations and their ability to operate autonomously in deep space, countering the idea that only terrestrial-based systems can provide reliable communications. 7. Global competitiveness in space. The idea that only established spacefaring nations can lead in space technology is challenged by China's rapid advancements in satellite technology. This suggests that emerging space nations can innovate rapidly and potentially redefine existing space exploration frameworks, which contradicts the notion of a static hierarchy in space capabilities. In summary, China's establishment of the DRO-based three-satellite constellation not only demonstrates advanced engineering capabilities but also provides numerous counterintuitive insights into the dynamics of space exploration, resource utilization, and the evolving nature of satellite technology. This project sets the stage for a new era of scientific investigation and operational efficiency in the Earth-Moon region and beyond. The establishment of China's three-satellite constellation in Distant Retrograde Orbit DRO is a landmark achievement that has implications far beyond its immediate technical accomplishments. While many reports emphasize the technical advancements and operational successes, certain aspects may be overlooked yet are significant for the future of space exploration and the strategic positioning of China in the global space race. Key overlooked aspects. 1. Strategic importance of cislunar space. The reports mention cislunar space as a domain for future exploration, but the strategic significance of this area cannot be overstated. This region extending up to 2 million kilometers from Earth is considered crucial for lunar resource exploitation, long-term human habitation, and as a launch point for interplanetary missions. Control over this space could provide advantages in terms of resource acquisition, scientific research, and establishing a foothold for future human activities on Mars and beyond. The ability to navigate and utilize cislunar space effectively will be pivotal in shaping the next phase of human space exploration. 2. Low-cost deep space exploration. The achievement of low-energy insertion into DRO using only 1/5 of the fuel typically required is a remarkable milestone that could redefine cost structures in space missions. While the reports highlight fuel efficiency, the broader implications, such as the democratization of space exploration, are less frequently discussed. Lower costs can enable more missions, potentially allowing for increased participation from private entities and smaller nations, thereby fostering a more collaborative approach to space exploration. 3. Inter-satellite communication breakthroughs. The successful validation of K-band microwave communication links over 1.17 million kilometers is a technological leap that could revolutionize how satellites communicate and operate in space. This capability not only enhances the operational efficiency of the constellation but also sets the groundwork for future satellite networks that could support global communication, navigation, and Earth observation capabilities. The implications for commercial applications and international collaboration in satellite technology are significant, yet often overshadowed by the focus on the scientific aspects. 4. Autonomous navigation and fault recovery. The development of a space-based orbit determination system that allows satellites to track each other represents a paradigm shift in how spacecraft can be managed. This system, which reportedly achieves the precision of traditional ground-based tracking with a fraction of the time and cost, could lead to more autonomous operations in deep space. The significance lies in its potential to reduce reliance on Earth-based infrastructure, thus enabling more resilient and adaptable mission planning and execution. This could be particularly vital in scenarios where immediate communication with ground control is not feasible. 5. Scientific research opportunities. Beyond enabling lunar exploration, the stability of the DRO presents unique opportunities for scientific research in quantum mechanics and atomic physics. The reports mention these fields, but the potential for groundbreaking discoveries in fundamental science due to the unique conditions offered by the DRO is a significant aspect that could reshape our understanding of physics and the universe. The ability to conduct experiments in a low-gravity, stable environment opens new avenues for research that could lead to technological advancements with terrestrial applications. 6. International collaboration and competition. The establishment of this constellation also raises questions about international dynamics in space exploration. While the reports highlight China's advancements, they do not thoroughly explore the geopolitical implications. As nations vie for dominance in space, China's achievements could prompt responses from other spacefaring nations, leading to both competition and potential collaborations. Understanding these dynamics is crucial for predicting the future landscape of international space exploration and cooperation. 7. Long-term vision for space infrastructure. The concept of a DRO-based spaceport as proposed by the Chinese Academy of Sciences signals a long-term vision for space infrastructure development that is not fully elaborated in the reports. This infrastructure could serve as a launch point for deeper space missions and facilitate the establishment of permanent human presence beyond Earth. The strategic planning involved in constructing and utilizing such infrastructure could be transformative for future interplanetary travel and habitation. Conclusion. While the technical achievements of China's 3-satellite constellation are indeed significant, the broader implications of these advancements, ranging from strategic positioning in space to the potential for collaborative exploration and scientific breakthroughs, are crucial elements that deserve more attention as nations continue to explore the cosmos. Understanding these dynamics will be essential for shaping the future of humanity's endeavors beyond Earth. The DRO constellation not only represents a leap in engineering and technology but also sets the stage for a new era of exploration that could redefine our relationship with space itself. The establishment of China's three-satellite constellation in the Earth-Moon region represents a landmark achievement in space exploration and technology. Here are 4 invaluable points for in-depth analysis and discussion. 1. Advancements in Distant Retrograde Orbit DRO technology. China's development of the first three-satellite constellation based on Distant Retrograde Orbit DRO marks a pivotal moment in space exploration. The DRO offers a unique orbital configuration that allows spacecraft to maintain stability with minimal fuel consumption. This characteristic not only enhances the sustainability of space missions but also serves as a natural hub for future explorations connecting Earth, the Moon, and deep space. The implications of this orbit are profound as it reduces operational costs and increases accessibility to cislunar space, paving the way for extensive scientific research and potential resource exploitation. 2. Fuel efficiency and cost reduction. The satellite's ability to achieve low-energy insertion into DRO using only 1/5 of the fuel typically required for such maneuvers is a groundbreaking achievement. This significant reduction in fuel consumption not only lowers the costs associated with launching and maintaining satellites but also sets a precedent for future missions. The financial implications of such efficiency are vast, potentially allowing for more frequent and elaborate space missions without the burden of exorbitant costs. This advancement could democratize space access, facilitating both governmental and commercial enterprises in the exploration of the Earth-Moon region. 3. Innovative inter-satellite communication and navigation systems. The successful establishment of K-band microwave communication links over a distance of 1.17 million kilometers demonstrates a significant technological breakthrough in satellite communications. This capability is crucial for constructing large-scale constellations in cislunar space and enhances the potential for coordinated operations among multiple satellites. Furthermore, the implementation of a space-based orbit determination system allowing one satellite to track another replaces traditional ground tracking methods and achieves precision comparable to those methods within a fraction of the time. This innovation not only lowers operational costs but also enhances the efficiency and reliability of satellite navigation and communication, crucial for future exploratory missions. 4. Strategic implications for future space exploration. The strategic significance of the Earth-Moon region cannot be overstated. With the potential for lunar resource exploitation and the feasibility of long-term human habitation beyond Earth, the establishment of this satellite constellation lays the groundwork for sustained human activities and exploration in cislunar space. This mission is not only a technological triumph but also a stepping stone towards broader interplanetary exploration goals. By fostering collaboration among international space agencies and private enterprises, this initiative may lead to advancements in space science, including astrophysical research and fundamental scientific inquiries into quantum mechanics and atomic physics. In conclusion, China's three-satellite constellation project in the Earth-Moon region encapsulates a convergence of technological innovation, cost efficiency, and strategic foresight that could redefine the landscape of space exploration. Each of these points offers a rich avenue for further exploration and discussion on the future of human activity in space. Here are 3 famous historical cases of significant advancements in space exploration that are comparable to China's recent achievement with the three-satellite constellation in the Earth-Moon region. 1. Apollo Program 1961–1972. The Apollo program was a pivotal series of missions undertaken by NASA, culminating in the first human landing on the Moon on July 20, 1969 with Apollo 11. This program not only successfully demonstrated the capabilities of human spaceflight beyond low Earth orbit but also established techniques for lunar exploration, such as the use of lunar modules for landing and takeoff. The Apollo missions involved sophisticated navigation and communication technologies, With Apollo 13 famously showcasing human ingenuity in crisis management when an in-flight malfunction nearly led to disaster. The program's success laid the groundwork for future lunar and planetary exploration. 2. International Space Station 1998-present. The International Space Station ISS represents one of the most significant collaborative achievements in human space exploration. Launched in 1998, the ISS is a multinational project involving space agencies from the United States NASA, Russia Roscosmos, Europe ESA, Japan JAXA, and Canada CSA. The ISS serves as a unique research laboratory in low Earth orbit, facilitating experiments in microgravity, life sciences, and technology development. It also represents a platform for international cooperation in space, paving the way for future missions beyond low Earth orbit, including plans for crewed missions to Mars. 3. Mars rover missions 2004-present. NASA's Mars rover missions, particularly the Spirit and Opportunity rovers launched in 2003 and the more recent Curiosity 2011 and Perseverance 2020 missions, have significantly advanced our understanding of Mars. These rovers have conducted extensive geological surveys, searched for signs of past life, and gathered data on the Martian climate and atmosphere. They have demonstrated the capabilities of autonomous navigation and operation on distant planetary surfaces, similar to the advanced technologies utilized in China's 3-satellite constellation. The upcoming Mars sample return mission, which aims to bring samples back to Earth for analysis, is a testament to the ongoing evolution of interplanetary exploration. These historical cases illustrate the trajectory of human space exploration, showcasing how advancements in technology, international collaboration, and innovative mission design have paved the way for future exploration. Much like China's recent endeavors in establishing a 3-satellite constellation for Earth-Moon exploration, China's establishment of the world's first 3-satellite constellation in a distant retrograde orbit (DRO) is a groundbreaking achievement that sets the stage for a new era in space exploration, particularly in the Earth-Moon region. This development, spearheaded by the Chinese Academy of Sciences (CAS), carries significant implications for future lunar missions and deep space exploration. Below are predictions for the future based on this technological advancement. Enhanced lunar exploration capabilities. 1. Support for future missions. The 3-satellite constellation will play a crucial role in upcoming lunar missions by providing high-precision navigation and space-based inter-satellite measurements. This capability will facilitate more efficient orbit determination and autonomous navigation, crucial for landing and operating on the lunar surface. 2. Increased scientific research. With the DRO's stability, researchers will conduct advanced scientific studies, including investigations into quantum mechanics and atomic physics. The data gathered could lead to breakthroughs in our understanding of fundamental physics, further enriching our knowledge of the universe. Cost-effective space operations. 3. Reduced mission costs. The innovative design that allows for low-energy insertion into DRO significantly decreases fuel requirements, thereby lowering the costs of accessing cislunar space. This cost-effectiveness could make lunar exploration more accessible, encouraging both governmental and private sector investments in space missions. 4. Expansion of commercial activities. As operational costs decrease, the potential for commercial activities in cislunar space will rise. This could lead to the establishment of lunar bases for resource extraction, tourism, and even manufacturing, creating a new economy in space. Strategic and geopolitical implications. 5. Leadership in space exploration. China's advancements in establishing a DRO satellite constellation position it as a leader in cislunar space exploration. This could shift geopolitical dynamics, prompting other nations to enhance their investment and participation in space exploration to remain competitive. 6. International collaboration. The complexities of space exploration may encourage international partnerships. Countries may seek to collaborate with China to share data and technology, especially regarding lunar habitation and resource utilization. Infrastructure development in cislunar space. 7. Establishment of spaceports. the concept of a DRO-based spaceport may become a reality, facilitating not only lunar missions but also interplanetary exploration. Such infrastructure would serve as a staging ground for missions to Mars and beyond, supporting long-duration human presence in space. 8. Communication networks. The successful validation of K-band microwave communication links between the satellites sets a precedent for establishing robust communication networks in cislunar space. This infrastructure will be critical for coordinating missions and enhancing communication with lunar surface operations. Innovations in space technology. 9. Advancements in satellite technology. The developments achieved through this project may lead to innovations in satellite design and operations. The satellite-to-satellite tracking system could inspire new technologies that improve navigation and timing in various orbital environments, not just in cislunar space. 10. Autonomous systems. The success of autonomous navigation systems will likely drive further research into AI-driven spacecraft. This could lead to more sophisticated autonomous operations in deep space, enhancing mission success rates and reducing the need for human intervention. Long-term human presence beyond Earth. 11. Preparation for lunar habitation. The research and data collected from the constellation will inform strategies for long-term human habitation on the Moon. Understanding the lunar environment will be essential for developing habitats and life support systems necessary for sustained human presence. 12. Resource exploitation. As lunar exploration progresses, the potential for resource extraction such as water ice and rare minerals will become a focal point. The DRO constellation can aid in mapping and assessing these resources, enabling future missions to exploit them efficiently. Conclusion. China's pioneering efforts in establishing a 3-satellite constellation in DRO represent a significant leap forward in space exploration. The implications of this advancement are vast, spanning enhanced lunar exploration capabilities, cost-effective operations, strategic geopolitical dynamics, infrastructure development, technological innovations, and the groundwork for a long-term human presence beyond Earth. As these predictions unfold, they will shape the future landscape of space exploration and utilization, potentially making cislunar space a new frontier for international collaboration and commercial enterprise.